Hello and welcome to this presentation. The topic is IPNES, Interpreted Petri Net for Embedded Systems. At the beginning, we'll make some short introduction to the embedded system modeling and synthesis. Then the model-driven design and IPNES model. Next, research results. Finally, the conclusion and the further research. Nowadays, there is observed a dynamic increase in the use of various types of embedded systems. They are applied in virtually every aspect of modern society environment, from mobile devices and simple processes control systems, through the Internet of Things and Industry 4.0, to highly specialized systems applied in areas of healthcare and diagnostics. Microcontrollers used in such systems are becoming more and more complex and complicated. This implies increasingly more complex implementation, longer development process, and finally it takes more time to launch the product on the market. In addition, the architecture of currently produced microcontrollers often includes several CPU cores. This allows carrying out many independent operations concurrently. On the other hand, it causes a further increase in the complexity of the implementation related to the concurrent processes synchronization and the data exchange. So if we point out the main problems of single or distributed embedded system implementation, we've got the complicated and time-consuming process of design, implementation and verification, complicated process of reconfiguration or extension of existing embedded system, integration of different hardware architectures. An example when we have to use some different microcontrollers, DSP, FPGA or some PLC devices in one distributed system, the high cost of the control system based on PLC networks, and finally the proficiency in programming, especially when we have to use the hardware description languages. One of the common approaches to speed up embedded system implementation is to use behavior models. They are applied to present and analyze relations between the objects. Hence, they are often used in the design methods called model-driven design. Specific model transformation allow carrying hardware synthesis, as a result of which either some code fragments are generated or even entire implementation of the embedded system. This saves a lot of time that would have to be spent on manual implementation by the designer. The behavior models have different properties and applications. Model-driven design is usually divided into several stages. Here we can see one of the implementation paths. First, we've got the model. It is a design stage where the designer provides a behavior model of his system. Next, we've got the decomposition. In this stage, the model is divided into several end models. Furthermore, some optimizations like separation of repetitive processes are provided. This stage can be performed either manually or automatically. The third stage is the automatic code generation for the target device. Finally, the fourth stage, we've got the entire system and we can make verification. Our paper focuses on the first stage, so this is the model. We propose a new model called Interpreted Petri Net for Embedded System, IPNES, for describing the behavior of any embedded system. This model allows to describe both a single model system and a fully distributed system that requires process synchronization and the data exchange. This model contains a number of different elements that are necessary for operating of any embedded systems, such as places, transitions, the directed arcs which connects places and transitions, inputs and outputs, shared variables, time parameters, and the user's code. The definition of the IPNES provides several functions like initial marking, assignation of the input alphabet to transitions, assignation of the output alphabet to the places, assignation of the shared variables to the places, time parameters to the places, user's code to the places, and outputs to the transitions, shared variables to the transitions, and finally places to the transitions. That's the main definition of the IPNES. Here we've got some examples of graphical notation of IPNES. So we've got the places with the marking and the transitions with some parameters of the conditions. On the other figure there's shown some output, shared variables, and so on. At the bottom we've got the example of some simple control system. In addition to the proposed formal model of IPNES, we also had to be able to save this model as text for further processing. Therefore, we also proposed a new text description model, which we called PNML-ES. It is based on the PNML language. However, we had to extend it by additional tags like defining target system, forcing the assignment of places and shared variables, handling conditions for the transitions, user's code, time parameters, and so on. Here we've got the example of the PNML-ES. As you can see, the PNML is based on the XML text. If we look deeply, we can see the model definition. It uses the hardware of the Raspberry Pi 3. The code will be generated as task in the C language. We've got some inputs and outputs of this model, the definition of the communication protocol, which will give the data exchange between the end models in the system. Finally, here we've got the places and transitions and so on. So here we've got the place P1 with the initial marking, the arcs and the transitions with the input x1 condition, so the x1 should be greater than 125. The best example is the one of a real system. We've got some house with several end devices responsible for specific functionalities. Now we want to connect them to provide a distributed embedded system which will be work as a smart home. As we can see, we've got different models like air conditioning model, water valve, some room lights and window blinds, and so on. Each of them needs some inputs to do the job. Some of them have to be taken from the other models, like we can see. So here we've got the light sensor as input in room lights, but the light sensor output is here in the window blinds. In the next stage, this IPNES model is processed by the automatic decomposition algorithm, which divides whole process to each end model. Furthermore, it provides variables for data exchange and process synchronization between end models. As you can see, process now gets some temporary places and some synchronization conditions. Finally, after the decomposition process, we can use an algorithm to automatically generate code for individual end models. As you can see, for a smart home system, the use of IPNES model allows the use of various hardware architectures. In example, we've got some Z-board Zinco 7000 where the code is generated in the Verilog, then some Arduino Leonardo where the code generated in C, then again Zinco 7000 which the VHDL code is the base, The late Panda, where the operating system is the Win IoT, and the code is generated also in C. The Linux as the base of the operating system, and the code generated in C in Arduino Uno, and the FreeRTOS and the STM Discovery. So the code here was generated as C task. As you can see, there are many of the operating systems architectures and the code, the generated code, which finally works together in the distributed embedded system. Here you can see the table with comparison of the behavioral models features in the context of the suitability for the distributed embedded system synthesis. The FSM-based models do not natively support concurrency. The UML-based models generally support concurrency. However, due to their origin and format description, they are also difficult to apply in the case of distributed embedded systems. The classic Petri Net does not support any hardware-related items. The hierarchical Petri Net enables a rich description of concurrency system. However, due to its complex structure, it is complicated, which makes it difficult to implement the next steps of the synthesis, i.e. the decomposition and description. The IOPT, it also has a very extensive description, and it allows to stay more than one token in a place. Furthermore, communication between nodes takes throughout special channels. Thus, these models hinder or do not allow the synthesis of the distributed embedded system. Finally, the IPNES has a less rich description, e.g. there is no hierarchy or the capacity of the places is limited to 1, but it provides balanced ratio of features and the simplicity of the description and the subsequent stages of the synthesis. On the 3 next slides, we show some research results of resource usage. We compare the IOPT tools with our Embed Cloud tool for the single end model embedded system. We provided simple models and bigger generated automatically with 10 to 1000 places. Here we've got the diagram with the program memory usage. Maximum use of program memory was noted for the IOPT tool, and it was around 204 kilobytes. And for the Embed Cloud, it was around 19 kilobytes. The differences are between 10 to 900%. The biggest differences are for the biggest tests were 100 of places. On the next slide, we can see the dynamic memory usage. Both tools generated similar dynamic memory usage. It was around 1 to 1.5 kilobytes. The differences are between 10 to 27%. And the last one is the reaction time. The greatest advantage of the Embed Cloud over the IOPT tool can be seen with the largest models containing hundreds of places. The differences ranges from the 26% to the 95%. The maximum code generation time for the 1000 places was for the Embed Cloud, it was around 3 seconds, and for the IOPT tools was about 5 seconds. So for the conclusion, proposed model allows eliminating the manual implementation and provides significant reduction of the implementation time. Furthermore, it simplifies the reconfiguration and integration of different hardware architectures and operating systems in the distributed embedded system. The obtained research results were comparable or better than other methods from 10 to 900%. Further research will be concentrated on the optimizing algorithms to reduce the amount of the resource usage, implementation of the publicly available web application, increasing the number of natively supported architectures, and the implementation of the fault-tolerant control algorithms. Thank you for your attention.